In this video, we're going to kind of formally define a definite integral. And once we learn how to actually evaluate integral functions, we won't need to take into consideration a lot of what we're learning today. What we're learning today is how we can visually see it based on a graph. So a couple things. When we're finding a definite integral, we're finding the area below the curve and bounded by the x-axis. So if we see the picture, areas below the x-axis count as negative, and areas above count as positive. Now, once we actually start solving these without the picture, if I were to give you this guy here, you will get a negative answer. You don't have to do anything different. So the way we can do this is area below, we subtract, area above counts as positive. So a Riemann sum, again, estimates the value of this definite integral, which is the area under a curve. Those are all a similar thing. So this is kind of how we read all this. This is the integral. We say from a to b. We call these our lower limits or bounds, our upper limit or bound. This guy has to be here. We just read this as the integral of f from a to b. So here's our definition. Again, this definition is a little different than the one I showed you the other day. This is saying now, what if we take the width of each rectangle and make it approach 0, therefore turning it into an infinite amount of rectangles. But we're still adding up length times width of an infinite amount of rectangles, and that is equivalent, not an estimate anymore, but that is what an integral does. Continuity implies integrability. I really don't see this tested on the AP test, but this is similar to differentiation. If it's continuous, then we know it has to be able to be integrated. And again, this definite integral is equal to the area under a curve. It's not an estimate anymore. A Riemann sum is an estimate. So two special integrals, because I'm finding area. The area from one point to itself is 0. And that's because this is asking you to calculate the area between the line A and A, which is between that line and itself, and there is no area. When we calculate area backwards, so instead of calculating from B to A, if we were to switch that to go from A to B, since we're going backwards, my area gets counted as negative area. The additive integral property, this is just like our segment addition postulate from geometry. If I have some shape, here's A, here's B, here's C. If I ask you to calculate the total area from A to B, I'm asking you to calculate this total area. If you know part of it, let's say you know what the area is from A to C, so you know this piece, and then you also know the area from C to B is this piece. If we add those two areas together, we'll get the total area from A to B. So one way is to sketch a picture, and because we're finding area, my geometric formulas still apply if it's a geometric shape. So the function y equals 3 is a horizontal line. And this wants me to calculate the area from 1 to 4. So if I could calculate the area of that rectangle, that is also equivalent to the integral. And we can. Length times width. We know the height is 3 because this is the function 3. We also know the width is 3 because 4 minus 1 is 3. So one way to calculate this is just length times width. Obviously, most shapes are not going to be nice, pretty geometric shapes. Here we have another one. This guy is 4 minus x, so it's going to look like that. And they want me to calculate the area between 0 and 3. So my shape here is a trapezoid. So here I would use the formula for the area of a trapezoid to calculate that integral. Finally, now we're going to use our formulas for integration. So here, remember my rules for integration. If this is a sum, I can actually separate these. So I can really write this as the integral from 1 to 4 of x squared plus the integral of 1 to 4 of 3x plus the integral from 1 to 4 of 2. Also, remember, with coefficients, I can bring them out front. So this 3 can be written right here. Same thing with that 2. It can also be written there. And this usually isn't something that we'll write every time we evaluate an integral, but we can. And now, since I know specific values, I'm just plugging them in. So I know the area of x squared from 1 to 4. I know this piece is 21. Okay? Here, my 3 can drop down, and then I know the integral of x from 1 to 4 is 15 over 2. So we're literally just plugging these in. And then here, again, my 2 can drop down, and it gets multiplied by whatever the integral from 1 to 4 is. And that's going to be 3. And if I evaluate that, I get the exact value for the area under this curve. Here again, I'm just given some different information. Here they want to know the full value from 0 to 5. I don't know that, but I do know the value from 0 to 3. And so if I calculate the value from 0 to 3, and then I can add that to the area of 3 to 5, that additive integral property says that will give me the total area then from 0 to 5. Okay? Technically, we should be writing all of this in here. I'm just trying to save time. Okay? So the area from 0 to 3, we know is 7. And the area from 3 to 5, we know is negative 4. And then finally down here, this is kind of our starting point right here, and we're ending at 3. So it says we're actually integrating backwards because we're starting at 5 and we're ending at 3. So what I can do is I can rewrite this, and these are equivalent. When I go backwards, it changes the sign of my answer. So if I know this integral, I can just slap a negative in front of it. And we do know the integral from 3 to 5 is negative 4. So this negative drops, and this piece here is negative 4.